We're going to study one kind of example from section 1.10, so another application section, and we're just going to look at this situation called a linear difference equation example. And this is another nice application of what we've done. We're not going to solve a linear system here. What we're going to do is apply vectors and matrix multiplication to a situation that seems to have nothing to do with vectors in the usual sense as arrows or points in space. So this is also the application type that we will come back to later in the course and study in more detail. So let's read this example. So in 2020, the population of a certain city is 800,000 people, and the population of the surrounding suburbs is 500,000 people. Demographers estimate that each year 4% of the city population moves to the suburbs and 5% of the suburban population moves to the city. So this is going to happen each year, year after year. For some reason, they've determined that they think this is the pattern. Each year, 4% of the people move city to suburb, 5% of the people move suburb to city. So we want to estimate the population of the city and the suburbs, both populations, in 2021, 2022, 2023, over the next 3 years. So let's see how we can organize our information here. And let's see if this all fits. Yeah. So of course, in 2020, we know the city population is 800,000. Suburban population is 500,000. That's our sort of our starting point, right? What we want to do is we want to now express the city population in 2021 and the suburban population in 2021. Now, if we just wanted one of these, we wouldn't have to look for a pattern and all of this. We could just calculate it. But there's going to be a pattern, and then we're going to see that we can apply this pattern to any future year, basically. So let's see how we could calculate the city population in 2021. So I break it down into two groups of people, those who stayed in the city from 2020 and those who moved from the suburbs since 2020. Because a certain amount of the city people are going to leave. So we know 4% of the city population leaves. So 96% of the city population stays. So I can write this as 0.96 times 800,000 will be the city population that's left. Plus the people who move from the suburbs, I think 5% of the suburban population moves to the city. So that's going to be 0.05 of the 500,000. And we'll add that up, figure that out in just a second. But right now we're just looking for patterns here. With the suburban population in 2021, we can do a similar calculation. And here, I don't know, I wrote those who move from the city first. There's no rule about which term goes first here. Okay, things just line up nicer for me if I keep city here, suburb here. But you could have written either term first. So if I look at those who move from the city to the suburbs, that's going to be 4% of the city population. So that's 0.04 times 800,000 plus those who stayed in the suburbs from 2020. So we know 5% of the suburban people moved away, so 95% of the 500,000 are still in the suburbs. So that's nothing too profound there, right? Now, but the way these numbers are arranged is like matrices and vectors give us a nice way of organizing this information. Now, watch what we can do. So we're going to call x sub k, this is a vector quantity. It's going to be a 2-entry column vector. City population k years after 2020 over suburban population k years after 2020. So x0 is just our initial situation in populations in 2020. It's a column vector with entries 800,000, 500,000. And really, we could express this problem. What we want to do is we want to calculate x1, x2, x3. And so let's go ahead and do that. And I'm just going to shift this sheet up a bit. So x1, which are the populations in 2021. Now, we already wrote down, just moments ago, expressions for those populations. And so I'm just going to recopy that. So I have 0.96 times 800,000 plus 0.05 times 500,000. And that's the first entry. The second entry is going to be 0.04 times 800,000 plus 0.95 times 500,000. And we can express this as a sum of two vectors, since when we add vectors, we just add corresponding entries. 0.96, 800,000, 0.04, 800,000, 0.05, 500,000, okay, 0.95, 500,000. And now each one of these two separate vectors can be expressed as a scalar multiple of the first one of 800,000. I could factor out a 800,000 times the column vector 0.96, 0.04. And I could factor out a 500,000 from the second times the column vector 0.05, 0.95. Okay. Now, so far, it's just sort of okay. But now here's where we can really apply something we've talked about. We've talked about what it means to multiply a matrix times a column vector. So I can think of this as the product of a matrix times a column vector, where the columns of the matrix are 0.96, 0.04, and 0.05, 0.95. The column vector that I'm multiplying by is 800,000 and 500,000. Uh-oh. So what we're seeing here is x1 can be thought of as this matrix 96, 0.04, 0.05, 0.95 times x0. We can take a column vector that represents the 2020 population and multiply by this matrix of probabilities. Okay. And we get the populations in 2021. There's a word for this. This is called a migration matrix. And like the 0.96 represents the percentage who stays in the city, 0.04 who leaves the city for the suburbs. 0.05, the percentage who leaves the suburbs, go to the city. 0.95, percentage who stay in the suburbs. And so it's sort of, let's just call this M. So x1 is equal to m times x0, and you can just plug the numbers into a calculator here. I got 793,000 and 507,000. Okay. And that's the city suburb 2021 populations, right? Now to get X2, do you see, we could do the same thing. We could actually take 793 and 567 and just put them in the positions that 800,000 and 500,000 had in our first part of the calculation. But we're not going to do that again. This just amounts to taking the migration matrix times x1. So we can use that same migration matrix again, because that same trend applies year after year, multiplying by the population in 2021 to get the population in 2022. And so let's see, x2 is let's see, what do we want? We want 2021, 2022. So I have 786, 630, and 513, 370. And again, that's city population, suburban in 2022. And of course now it's nothing exciting now. We're going to get x3 by taking m times x2. And that's 780, 833, and 519, 167. So there we have my city and suburban population in 2023, according to this demographic model, right? Now, really we're just going to observe that we're almost through, that x k plus 1 vector is equal to m x sub k, and this is called a linear difference equation. We're not going to really talk about these anymore, but if you ever see this phrase out there in the world, this is what someone's talking about. Actually, we are going to come back to this later in the course, because the one question here I'd like to leave you with is there a trend? As the years go by, are these populations going to keep changing, or are they going to stabilize in some way? In other words, if we computed x4, x5, x6, x7, x8, is there a limit to this process, limit in the sense of calculus, or do the populations keep changing? And I'm just going to leave that as an open question, because we're going to come back and talk about this some more later in the course.